The first topic will be given by Professor Simon Petrovic and Professor Andrew Watson. And the topic is about the turbogenerator energy recovery model. Professor Simon Petrovic is from the Aeronautical and Automotive Engineering, Loughborough University, United Kingdom. His speech title is Turbogenerator Energy Recovery Model. Okay, so Professor Petrovic and Professor Watson, could you share your screen to start the presentation?
Okay. Yep, just doing that now.
这个屏幕是我这边控制吗？啊，可以。这应该是他的屏幕。OK。这个是咱们的屏幕吗？他的啊 ，OK。Okay, Professor Petrovic, are there any problems with the video or?
Okay, can you see the video?
Yeah. You can start the presentation by the video or by yourself. Is both okay? Yeah.
Okay. Can you actually see my screen?
Not yet. Yeah, we can only see the file of the download file of your Windows system.
Yeah. Let me do something else. Is that better?
Yes.
Can you see my screen?
Yeah.
Okay.
Yes, we can see the screen. Okay. That's it.
I'll just fast forward a little bit.
Mm-hmm. So no voice, I think. Yeah.
You have no voice?
Yeah, no voice. Mm-hmm.
Okay. I can hear it from my side.
Mm-hmm.
Okay.
Okay. So when you share the screen, please check some checkbox. There is a choice for sharing the voice. Yeah. So share the screen and also share the voice. Then we can hear.
I'll share sound. This one. Let me try this again.
Mm-hmm. Okay.
Hello, my name is Simon Petrovic.
Yeah.
I'm a researcher
Okay.
at the
That's working.
Yeah, that's it.
Okay. Good.
Mm-hmm.
I will talk today about energy recovery for combustion engines, including HEVs or hybrid electric vehicles, in particular with a turbogenerator or TG device. This work started off as
could the voice a little be louder?
UK, plus other industrial partners, but the most recent work has focused more on simulation and controls development.
Yeah. Okay, thanks.
Contents. The presentation will look at motivation.
Yeah,
Why
okay,
do we
perfect.
need
Thanks.
Okay.
waste heat recovery device? Benchmarking from passenger car to heavy duty. The design of the low pressure turbine device and its characteristic map, as well as an indication of how much thermodynamic power can be recovered. For controls and simulation, a simplified CISO or single input, single output controller is developed in 1D simulation and in co-simulation. The simulation is performed at steady state as well as in transient operation. Finally, conclusions and recommendations are presented. Motivation. Looking at a typical Sankey efficiency diagram, it can be seen that the ICE or internal combustion engine does not have more than about 35 to 40% peak efficiency. This inefficiency is manifested as waste heat, some of which can be recovered. The amount recovered depends upon pressure loss from the muffler to tailpipe, TG efficiency and back pressure impact. Better system efficiency implies more zero emissions kilometers for HEV applications. Further motivation. The basis of this work is to use the LPT developed by Imperial College in collaboration with Ford and to estimate what the benefit would be on a drive cycle, in this case the NEDC or New European Drive Cycle. Reference paper is supplied for background reading. The simulation study targeted a 2-litre gasoline engine and used steady-state vehicle calibration data to calibrate the simulation model. A simple SISO single input, single output controller was built to demonstrate the benefits. An initial key point analysis was used with a sensitivity analysis and a knock assessment, followed by a full co-simulation using WaveRT and Simulink. Benchmarking. There is a range of devices available. Heavy duty or HD applications, for example, Bowman Power, use a TG device. The use cases are more steady-state motorway driving with minimal transients. Some turbo compounding cases, like Scania, where the TG device is mechanically coupled to the crankshaft. For passenger car applications, the usage is more limited. For example, the Valeo CPT Tigers recovery system or the decoupled Aerostech solution, which has no mechanical shaft linkage between the turbine and the compressor. Finally, electrified turbochargers, for example, Borg-Warner turbocharger systems BWTS, have e-machines directly integrated into the device, permitting a shifting of operating point in order to recover electrical power. LPT location. From the full engine mapping, thermodynamic power can be calculated downstream of the conventional three-way catalyst, which is the best location for a TG since catalyst light-off is not compromised, and the device can be bolted on as an aftermarket device, for example. The calculation of the thermodynamic power is shown. Engine dynamometer mapping data is shown here, and for example, the maximum pressure post-catalyst is 1180 hectopascals at 6,500 RPM. Low pressure turbine. The LPT is optimized at low pressure ratios. For example, in this range 1.05 to 1.3. Its peak efficiency is high, being about 70%, and the efficiency map is shown from a prototype build at Imperial College, which was tested on an engine. It turns out that around 1 kilowatts for the high boost 1.0 litre EcoBoost GTDI engine was available, and this led to a 2.4% BSFC reduction at peak torque. But the question remains, can the LPT power be increased without compromising system BSFC? Model layout. The simulation model was developed in Ricardo Wave. Some of the model parts include the throttle controller, which controls the BMEP or the engine torque, the tip or throttle inlet pressure controller, which uses the wastegate to control the intake manifold conditions. Connected downstream of the conventional turbocharger wastegate is the LPT plus the wastegate, and the wastegate control, the low pressure turbine wastegate control, controls to a pressure ratio set point of 1.15. Key point determination and results. The key points are based on drive cycle residency determination and are used to predict the possible energy recovery. Key points are listed. Altogether there are 16, and number 16 is, for example, 2,500 RPM and 11 bar. So this is the most highly loaded point. It turns out this point alone gives a 2.3% fuel consumption improvement. A generic controller would keep the TBV fully open until about 1750 RPM or 7.5 bar BMEP, since there is only a small amount of energy recovery possible. This would be a control system requirement. Key point sensitivity. In this case, 2 operating points were selected which are non-NEDC and are more representative of real-world conditions. Then there was a sweep of the low-pressure turbine bypass valve from fully open to fully closed. It can be seen, for example, at 3000 RPM 13 bar BMEP, that in theory we could recover up to 3.6 kilowatts of thermodynamic power, but there is a small increase in back pressure, and this needs to be traded off against other system requirements. Knock assessment. The knock assessment is based on Duaoud and AZAT metric as a function of the unburned fuel mass. 3000 RPM 13 bar and also 2000 RPM were selected as key operating points. In summary, there is no significant knock risk. It can be seen that at 3000 RPM and 13 bar there is a very small amount of knock intensity, which is effectively insignificant. co-simulation in real time on the NEDC. The co-simulation of the turbogenerator controller was performed on the NEDC drive cycle. There is good closed-loop control of the map and brake torque, as well as the LPT pressure ratio. However, the LPT opening was limited to 10 mm opening. The baseline results are in good agreement with real-world vehicle measurements, and so is the key point method. A summary of the results is shown, and it is indicated that the low-pressure turbine fuel consumption improvement over the whole cycle for maximum energy recovery equates to about 280 watts of thermodynamic power, and that is the average over the whole drive cycle. Finally, there are some cases to improve the energy efficiency further. On vehicle deceleration, the LPT TBV is fully closed. Summary of potential benefits. As a summary, the potential benefits are listed here. The main one is the fuel consumption benefit, which requires a capable transient controller. Further enhancements include VCT or variable cam timing, calibration modifications, and the interaction of the LPT turbine bypass valve with the conventional wastegate, which suggests a more advanced controller architecture is needed. There are no serious knock issues. Catalyst light-off can be improved with the dual benefit of recovered energy and the possibility to drive external EGR where available. Conclusions and further work. It has been demonstrated both in steady state and in transient control that the LPT system can give a fuel consumption improvement. However, more calibration and optimization is required to harness the full potential, which can include VCT enhancements and the interaction of wastegate and LPT TBV. The NEDC is a low load drive cycle where the overall benefits are small, but from key point analysis, a higher loaded drive cycle like the current WLTC should yield more energy recovery possibilities. Future work revolves around building a more advanced multiple input, multiple output controller to take advantage of the system interaction. Although a physical prototype of the TG was built for a small engine, an enhancement would be further hardware optimization and engine testing on this device. Thank you very much for your attention. Acknowledgements here show that it was a global team effort.
That concludes my talk. Thank you very much for listening.
Mm-hmm. Okay, thank you for the wonderful presentation about the turbogenerator model. So, are there any questions to Professor Watson? Professor. Okay, I may have one small question about the co-simulation of the real-time controller. I see there are for this simulation, the model is not only contains some basic dynamic properties of this turbogenerator, but also some details like something like open valve distance. I'm not sure. So could you show us some more details about this model? Because I think it is very challenging to develop a control-oriented model that also contains some necessary details about sensors activities.
Yeah. So can you still see my screen?
Yes. Oh, yeah. Okay. Yeah. That's.
Yeah. So it's basically contained with yeah. This doesn't show the whole co-simulation, but this slide shows basically the layout of the model in the Ricardo wave part. So what for the co-simulation, we've taken out the controller part, so the throttle controller, the throttle inlet pressure controller, that they've been taken out, and and also the bypass valve controller for the turbogenerator. So that's been taken out and put into Simulink. So that the way it's been done is that yeah, the 1D modeling is contained within Ricardo wave, and then the control part and the calibration. So things like yeah, the settings for the set points, like the air path settings, like the manifold air pressure set point, or the burn rate for the combustion. They are actually calibratable within Simulink. So that's used the steady state dynamometer calibration for that particular engine.
Okay.
So that this method really it's very generic.
Okay.
So it doesn't have to be just this engine.
Okay. So that means the core part of the system is generally based on static empirical model. Am I right? Or it also contains some physical models like the burning, or like the fluid dynamics process, something like that?
Yeah, I mean that combustion process, that's included here. So there are dynamics with the manifolds, for example. So you do get that dynamic, yeah, dynamic air path, and also the heat transfer to the exhaust.
Okay.
So that there are dynamics included there.
Okay. Clear. Thank you. And one more question is about the Ricardo wave. So is a specific software developed by Ricardo, or something like some other platforms?
Yeah, it's a commercial package. So the basic software is called Ricardo Wave, which is just this environment here. But then you have also the Wave RT, it's called, real time.
Okay.
Where you can do the co-simulation with Simulink.
Okay.
So I don't have a slide for that, but it's possible to do that with an additional package within the Wave family called Wave RT.
Okay, clear. Thanks very much.
Thank you.
So if there's no more questions, yeah. Okay. Thanks, Professor Anderson. So maybe that's all for this presentation. So if there are no more questions, we will turn to the next presentation.
Thank you very much.
Okay.
Thank
thanks.
You.
Yeah.